All right, in this discussion, I am going to go over green buildings and sustainability in buildings. Um, as you can see by this image, buildings have a major impact on resource use in the US. About 12% of all the water use in the country is used by buildings or inside of buildings. About 40% of CO2 emissions, 65% of waste output, that includes construction waste as well, and about 70% of electricity consumption. All of this is the percent of the total that's due to buildings. So 65% of all waste in the United States comes from buildings. So they have a major impact on our resources and sustainability. So I want to kind of lay that out there. Like, excuse me, buildings are really important. Also, kind of a well-known statistic is that humans spend about 90% of their entire life inside of a building. 90%. So that includes obviously working and living and whatever else you're doing. So it's important that we have sustainable buildings. Okay, so in this first part, I'm going to go over passive solar design, and I'll briefly go over the difference between active and passive solar design, and then I'll provide details of the 5 passive solar design principles, um, and how they work to minimize energy use. And then also there are some information about ancient uses of passive solar design that I'll go over. And I want to be really clear at the outset that these are 5 of the design principles. You may read other sources that say there are other principles. They're all pretty similar. It just sort of depends a little bit on your frame of reference and if it's passive solar or regular passive design. So I don't want you to think these are like the universal principles, but all of these principles are widely regarded as passive design principles. Whether or not they're the only 5 is a matter of debate. Okay, so the difference between passive and active, and this is really, really important, so you want to jot this down. Passive design is using the surrounding conditions to reduce energy use in a building. Okay, so that's passive design. Just you want to think about wind flows and the temperature and where the sun's coming in and so forth. Okay, so passive is like you're just capturing the energy for most of the time. Sometimes you use the wind to sort of disperse some heat, that sort of thing. But the point is, you're not actively um, like grabbing it or taking a solar panel and converting it or generating it. You're just sort of taking it from the environment. Okay. Um, and that's passive design. Passive solar design is really the use of these passive principles to capture and store the sun's energy. So we use the sun's energy to our advantage. And the goal with passive solar design primarily is to reduce your energy use. So most of it's used for heating um, and sort of ways to prevent excess heating in hot times of year. Active solar design, however, is the use of devices to move heat around. So solar panels are technically active because you're taking sunlight from here, you're converting it to electricity, and then you're moving it wherever. Or you capture something and then you take a fan and then you blow it somewhere else, or you store it in a water tank like solar thermal, and then you move that water somewhere else. Okay, so that's active, like you're actively pushing heat around. Whereas passive is just like you're sort of letting it happen. You have your windows here, allow the sunlight in, and just let things happen. Okay, so that's active versus passive. And the 5 principles, I'll go over these in more detail, so don't worry about it right now. We have orientation, we have windows, aka glazing, shadings and overhangs, insulation and air sealing, and thermal mass. Absolutely essential to understand that all of these have to be used together to have truly passive design. You can reduce your energy use by having proper orientation in windows, and a lot of people do, but to have real true passive design, you need to integrate all of these together. Okay, and I'll provide details of this here in a minute. Okay, so number 1, we have orientation. Orientation is just compass direction, so which direction your building is faced. And in the northern hemisphere, where we are, your building should, the long end of your building, right? So the long end of your building should face south. Okay. Um, so east-west ridgeline means the long end, like the peak of your roof should be east-west. Um, and the I'm sure you hopefully have a sense of the reason for this And that is in the northern hemisphere, if you look at the path of the sun throughout the day and throughout the year, it's almost always south. So hopefully you know sun rises in the east, peaks at noon, sets in the west. Okay. And so when it rises through the east, right, from the east, okay, it's going to be south. So it's going to start out like southeast and then south southeast and then south. And then it's going to be south southwest, southwest, west, right? So the thing is here is south, right? So east west is here. All this down here is south of this building. Okay, so the sun is in the winter is always in the south. In the summer, it actually rises a little bit northeast because of the tilt of the Earth. Um, but again, it spends almost all its time in the south. So, probably by like 4 o'clock in the morning, or yeah, 4 o'clock. Excuse me, 3 or 4 hours after sunrise, whenever that is, it'll be south and then it'll still peak in the south. So the hottest sun is always due south of you. And almost the entire year, the sun is going to be like south-ish. Okay, so the sun spends almost all its time south of us. So if we want to capture the sunlight, we want our building to be faced toward the sunlight, and that's why we want to be faced south. Okay? Okay, so overhangs and shading. This is number two. So first we have orientation or azimuth. Number two is overhangs and shading. So if we're faced south, we can capture all this great sunlight. But if you think about it, we really don't want to do that in the summer, okay? Because it's hot already, and if we're trying to minimize our energy use in the summer or in any of the cooling season, we really don't want that extra sunlight in the building. And so there's a couple ways to prevent that passively. A really good one is to do overhangs. If you see this image here, so if we're faced south, okay, so if this is south over here, and you can see the sun at different times of year. So let me point this here. So this is south that way. Okay. So if you think of this overhang here, okay, and if you remember, if you notice in that previous sun path chart, in the winter, you see the sun is lower in the sky, and hopefully you have some sense of that. That's why it's actually colder in the winter because the sun passes through more atmosphere, but it's higher in the sky in the summer. Okay, and then all in between, like here's going to be your um, spring and fall equinox, right? So first day of spring, first day of fall. Okay, so the later in the season, okay, so the closer the winter, the lower the sun is in the sky, which means your sun angle is coming in at a lower angle, right? So this is my winter sun, right? So it's coming in like this, and you can see it goes right underneath that overhang, okay? So the sunlight can get in the winter. But in the summer, when the sun's higher, here's the thing, it's the sun is hitting this overhang, and think of all the sunlight hitting this like that, right? So this overhang is blocking that most of that sun, and the only sun that gets through actually doesn't hit the house. Okay? And so this will shade, this is the peak time of the summer, so in the morning and afternoon it's going to kind of come in sideways, but the point is if you have an overhang designed properly, you can prevent the warmest summer sun from coming in. Okay? You can prevent that warm, really warm summer sun from coming in. And allow the winter sun in. So super important. You prevent summer and you allow the winter in. The other thing you can do is you could plant a tree on the south side, a deciduous tree, right? So any number of tree species, and hopefully you know that deciduous trees drop their leaves in the winter. And so in the summer, it'll be full foliage and will block most of the sun. In the winter, it drops the leaves and it'll allow most of that sunlight through. You can also use things like grapevines and there's other types of arbors that you can build. But the point is you need to keep the sun, you don't want the sun hitting your building any more than it has to in the summer. And then in the winter, you want it to come through. Okay, so here's another illustration of that. Summer sun, you see this is kind of a unique type of overhang. And there's different ways to do this. Um, you can have really long, like this is a nice long ridge line here. This is kind of more traditional type of house. But you can see there's an overhang here, there's an overhang here, overhang here, overhang here. So the third design principle, okay, so we have orientation, face south basically. Overhangs and shading, so block the summer sun and let the winter sun in. The third one that's absolutely essential is windows, or our windows. Um, and so you just need to have a bunch of windows on your south side. It's really not all that helpful if you allow this winter sun to hit the side of your building, but there's no windows to allow it in the building. So it'll warm it up because it'll hit the side, but if you have good insulation and so forth, it's not going to warm it up that much. So really you want these windows like this, nice big south-facing windows that winter sun just comes in here, and then the summer sun would sort of hit and hopefully shade most of these windows. Okay, so windows are absolutely essential. Otherwise, you're just not going to get enough sunlight. You got to be really careful. You don't want to have too many windows on the east and north side of the house because the sun's never going to hit there directly, or very rarely going to hit there directly. And windows are very bad insulators. Okay. Here's just this image of a like environmental center in Denmark, and you can see this is big south-facing windows, and there's a bit of an overhang here. And then this actually has a green roof, but anyway, big south-facing windows. This was entirely passively heated, which was really cool. Okay, so that's number three. So number one is orientation. Number two is overhangs and shading. Number three is your windows. Number four is insulation and air sealing. This is pretty straightforward. If you want to keep the heat in the winter and prevent the heat coming from in the summer, you need a lot of insulation and good air sealing. Pretty straightforward. And the last one, number five, is your thermal mass. Okay, so thermal mass is one that's probably the least understood and the least used of all of these. And a thermal mass is just a material that takes a long time to heat up and cool down. Okay, and so if you think about having a floor, like this is a big thermal mass, this floor. So if you have these nice south-facing windows, let's say there's windows here on the south side, and you have the sunlight that comes in the winter. So what happens when you have a thermal mass is that sunlight hits the floor, and instead of like getting hot really quickly, like a tile would do, certain types of tile, like ceramic tiles would do, or engineered flooring, it slowly heats up. So what it does is this will slowly absorb that sunlight throughout the day. Okay, so remember you have winter sun coming in, it's slowly absorbing that heat during the day. But the real benefit is then at night when the sun goes down, it really slowly releases that heat. So this floor will overnight when the sun's gone will slowly release this heat all over. This whole floor will release heat, so it'll stay warmer overnight. And then the opposite happens in the summer. In the summer, if any warmth that hits this floor, um, it's not going to get hot really fast, right? It's going to sort of absorb a lot of heat before it really heats up, and then it'll slowly cool down at night. So what it does is it sort of mitigates the overall temperature changes in the house. Okay, and again, this needs to be used combined with orientation windows and overhang to really work. You need to have this in the sunlight in a south-facing wall with windows, right? Um, and thermomass, this is not, even though people don't use it a lot in green building per se, or in a normal building, it was really common, for I guess, well, hundreds of years at least. I don't know if it goes further than that. But if you've ever seen a hearth, right? So a hearth around a fireplace, most people have one of these if they have a fireplace. A hearth is a thermal mass, okay? So it's stone or brick, which is really good at absorbing heat. And the point of this originally was, if you have this fire going during the day, back in the days when we didn't have a bunch of, active heating, um, we just had a fireplace, like I'm talking like pre-electricity days, then this hearth would absorb the heat from the fire all day, and then at night when you turn the fire down, it would slowly release that heat out, and it would keep the building warmer overnight, right? So there's all these different thermal mass, basically anything that's heavy and dense. Things that aren't good, like wood and vinyl, engineered flooring, carpet, metal, they're really bad thermal masses. They just heat up quickly and cool down quickly. Okay? So those are the five design principles. Now we'll see, I'm going to show you a little video that demonstrates some of these in kind of a modern building.
We're designing the Honda Smart Home to achieve net zero energy goals, which means that on an annual basis, we'll be producing as much or more renewable energy as we consume from the grid. But it's not enough to just put a bunch of solar panels on the roof. We really want the house itself to be very energy efficient. So we started with a concept called passive design. This is an old idea, but we're really trying to optimize it by applying some very modern design tools. Passive design basically just means building your house to work with nature as much as possible, and this lets you really reduce the amount of energy that's needed for heating and cooling. So we're looking at how do you work with the local climate conditions, how do you position the house on the site for maximum efficiency, and then how do you build the outer layers, the shell that we call the envelope.
So real quick, notice you said working with nature instead of against it. That's that whole passive design principle that we talked about at the beginning. And you'll notice here we have some nice overhangs for the over the windows, right? So there's a little mini overhang here and a mini overhang here. So these are definitely passive design principles in action.
Davis happens to be a really great place to apply these passive design techniques.
We are in the valley, Central Valley, where our summers are quite warm, but most evenings in the summer cool down quite a bit. We can use that cool air at night to basically bring into the house and avoid the use of air conditioning the next day. This is the south side of the building here, and as you can see there's overhangs up above here and on the first floor which shade the high summer sun, so that keep the sun out from inside the house during the summer. But when the sun's angle in the wintertime, it allows that sun in to provide free heat. The envelope is the outside of the building that basically separates the indoors from outdoors. So that's your walls, your windows, your roof, your floor. So the elements of the house include a double stud wall, triple pane windows. The roofing material is a cool roofing material which reduces the amount of heat gain. The slab is fully insulated because we are heating the house and cooling the house through the floor, and we want all that heating and cooling to actually get into the space and minimize the loss to the ground.
So what we're doing today is we're sealing the Honda Smart Home here at Davis. And what we're using is a new technology that we're developing for sealing envelopes using an aerosol spray, and it is able to automatically seal buildings without a lot of the manual processes that go on in typical sealing. So we're using a blower door just to simply pressurize the building while we apply the spray. So the aerosol fog on the inside is kind of driven to the leaks by the airflow, because when you pressurize the building, the only place for the air to escape is through leaks in the shell.
California's goal is to build zero net energy homes by the year 2020. So this house is a really good example on strategies that we can use to meet California's zero net energy goals.
By using these passive design techniques, we're able to really reduce the amount of energy required for heating and cooling the home. This lets us use much smaller mechanical equipment that's also very efficient. So as a whole, we should be using about 75% less energy than a typical home. Smart passive design really is the first step to achieving your net zero energy goals.
Okay, so really good demonstration of modern passive design house. You see cutting energy use by 75%. Pretty nice to have utility bills that small, I can say from experience. No, say from experience of not having small utility bills, how nice it would be to have something that small. But as you can see, all of those techniques were in there. You had the air sealing, you had the insulation, you have windows, you have orientation. They didn't mention anything about thermal mass. I'm guessing that's a thermal mass based floor, like an earthen type of floor. I mean, it was concrete slab, so concrete is a thermal mass. But anyway, I just thought that was a good demonstration of modern use of these principles. Okay, so that was a modern use of those principles. And the ancient use, there was a reading that was posted on this. Not going to go over into a whole bunch of detail here, but Mesa Verde, you remember that Native American um, uh, village in, this is actually in Colorado. And so this is, I don't know how many hundreds of years old, but it's, over 1,000 years old. And this is actually carved out into the side of a cliff. And the big thing here is this is a south-facing cliff. And you can see there's a huge overhang. You see that overhang right there? And so they oriented this properly and utilized an overhang. And somehow somehow carve their buildings out of the cliffs side. Not really sure how they did that. In Greece, they would orient whole buildings, excuse me, whole streets, like city streets, would all be east-west to capture the sun, the south-facing facades. And there's some other interesting passive ones like these wind towers um, in Iran, and how they capture. Basically, they use the prevailing wind to pull cool air through the building, and that air is naturally cooled by water underneath the ground, which is pretty fascinating. They did that, and you can see these towers sort of capture the wind. And there was also ancient Rome, also, if you remember, was in there. They used orientation, and they also developed a type of glass as well. So this is not something that's new by any stretch. In a way, like they used to, we're kind of going, back to the future, so to speak, in that we used to build buildings like this a lot, and then we just kind of got greedy, right? Like we developed all these ways to, air conditioning and heating and different types of heating, like furnaces and heating appliances and so forth, and we just sort of slap buildings up wherever we feel like it. We don't worry about the orientation. We don't necessarily worry about the insulation, although it's getting better, and we don't worry about windows. I mean, and they're still building homes like this. Without these principles when really we've known about these principles for thousands and thousands of years. Okay. And I'm going to show you one more video here. This is one of my favorite case studies of a passively designed building. So the Honda Smart House was like a real modern, like everything's modern and using all this technology, modern technology. And this one is much more hand built. Okay, it's like a craftsman type of house. And you'll see that he discusses two things that we haven't discussed yet, and one is cob. Jot that down. Cob, which is just a mixture of clay and straw and sand. It's a natural material, and you can see behind him. This is actually um, a cob wall behind him, and you can see how there's that detail here with the bird, and actually this hearth for the fireplace that we talked about. That is cob, and cob is really cool because it's mostly clay and you can shape it to any shape you want it to be, but it's also a really good thermal mass. Okay, so that's cob. And the straw bale, this is actually a hybrid house, as you'll see. The north side has straw bales on it, or it's actually the walls are built with straw bales, believe it or not. And they're really, again, it's a natural material, a really good insulator, not a good thermal mass, but it's natural, it's non-toxic and all that sort of thing. You can build it locally. Okay, and so I want you to pay attention for those two things, and also the overhangs and shading and orientation. They're all in here.
This is cob. Cob gives you excellent thermal mass heat storage. So it's a critical part of a successful passive solar design. A building that's going to heat itself and cool itself as much as possible needs thermal mass as well as insulation. Here on the north side of the building, for better insulation, we use straw bale. Thermal mass, like Earth, is a completely critical part of an effective passive solar design. This is designed as a passive solar structure, so the thermal mass of the cob is on the south side of the building where the sun hits. You can't build a good passive solar house out of 2x4s and sheetrock and styrofoam insulation because you don't have the mass. So this is actually a hybrid structure. The part to the left of this wall is straw bale, and the part to the right is cob. Straw bale and cob hybrid buildings are very common. And
So here you can actually see that's the straw bale in the wall, right? So the straw bale's here. So there's framing and then there's straw bales. And that's, remember, the north side where the insulation is. So you can see there's not a lot of windows on this side. There are some, you want to have some windows, but so this is straw bale here. And then there's cob on the other side.
You tend to see is straw bale walls on the north side of the building where you most want your insulation, and cob on the south side of the building, the part that gets hit by the winter sun. So the cob can absorb the heat from the winter sun and re-radiate that into your building later to help warm it. That also makes sense because you tend to have most of your glazing, most of your windows on the south side. And if you want a whole lot of windows on one wall, straw bale ends up.
So you notice here, again with our overhangs, right? So big overhang on the south. And you notice where there's extra large glass door, and there's an extra overhang there, and that's meant, you can see it's actually in the shade. It's meant to block the hot summer sun on that door, right? So you can get kind of creative with your shading
But a
apparatuses.
difficult choice to do that with. Straw bale on the north, and you see these big, pretty flat walls without many windows. That's straw bale. And so that's one very simple and obvious hybrid system. Is something like straw bale on the north for insulation, cob on the south for sculpture and thermal mass. And this interior wall here, this is cob up this high, and the cob is here for thermal mass. It absorbs heat from the wood stove when the wood stove's going. It also absorbs sunlight directly in the winter coming through these windows. The midday sun shines on this cob and heats it up. The earth provides a lot of thermal mass, which heats up very slowly and cools down very slowly. So it's a really, really effective way to cool a house, particularly in a dry climate like this. Historically, if you look at hot desert architecture anywhere in the world, what you see is really thick masonry walls made out of earth usually or stone. Those walls hold the coolness from the nighttime and very, very slowly heat up during the day. The way we do it here, at night we open up all the windows and we let the cool night air come through the house, and that discharges any heat that's been stored up in the thermal mass during the hot day. And then in the morning we close up all the windows and just keep that coolness locked inside the building. In the winter, it works pretty much the same way, except of course you don't open the windows at night, you leave them closed. And the sun, the low angle winter sun shining in through the south facing glass, that heat is absorbed into the thermal mass. Really good place for that thermal mass is in the floor. So we do these earthen floors in most of our structures. This is just made out of clay soil, sand, and straw, and sometimes gravel. And it's about 4 or 5 inches thick. And so the winter sun coming through hits on the earthen floor. The floor heats up during the day, as do any thermal mass walls that are close to the south side of the building and are also hit by the winter sun. All that heat is trapped inside the building. And then at night, when the sun goes down and the air temperature drops, the heat works its way back out of the thermal mass and heats the space.
So really great example, I think, of a more like old school passive design using a lot of natural materials, hand built. You can see there's a lot of creativity that went into this. So I just think that's a great case study. Really, really exemplary of all these principles. Okay, so that wraps it up for our passive solar design lesson. So again, passive design and passive solar design captures solar energy to provide heat and minimize active energy use. So it's using the natural conditions, working with the natural conditions instead of against them. Remember, we have our 5 principles. We have orientation, shadings and overhangs, windows, insulation, air shielding, and thermal mass. They absolutely, to have a truly passive house, you have to have all of these working together. And you can minimize your energy use by using a few of them or even just one of them. But to really have a passively designed house, you have to use all of them. And remember, passive design, while it is a modern, we're sort of modernizing the concept, it is by no means a new concept. We've known about these principles for thousands of years, and we're only sort of just remembering to utilize them again. Okay, so that's it for this lesson.